Welcome to the second video in the series aiming to explain quantum physics from the ground up. In this video we will apply Boltzmann's theories and consider the consequences of them, particularly the Equipartition Theorem. In the last video we showed how Boltzmann was faced with the problem of the day. How can we ground the observed laws of thermodynamics in something concrete, like Newtonian mechanics? By then, physicists suspected matter was made of particles, but with trillions upon trillions of them, predicting the motion of even a single one was hopeless. Boltzmann's solution was not to start by looking at the individual particle, but by looking at the probability surrounding a collection of particles. He used the idea of counting microstates to combine statistics with mechanics, which led to this equation. The probability of a system existing at a specific energy level is exponentially less likely the more energy the system has. We know the general idea is correct, but we introduced this scaling factor alpha as we weren't certain on the exact measurements. Once we figure out what alpha is, we can find the exact statistical distribution of energy within a closed system, which will allow us to ground thermodynamics in Newtonian mechanics. So, how do we find alpha? Let's take a particle within a cube, moving at momentum p. The magnitude of p doesn't change if the energy in the particle is conserved, it just changes direction. The energy of this particle can be assumed to be entirely kinetic, which would be p squared over 2m. In the previous example, we looked at a mass spring system, which had just one degree of freedom. Its energy depended on a single quadratic variable. A free particle in a box is different. It has 3 degrees of freedom, momentum in the x, y, and z directions. Every momentum vector can be described as a combination of these 3 values, px, py, and pz. Momentum is a 3-dimensional vector, and just like any vector in space, its magnitude is given by the Pythagorean theorem. For a specific momentum magnitude, p, we could make a sphere of all possible microstates, that is, combinations of px, py, and pz values that result in the same magnitude of p. If you select a point on the sphere, you get a specific value of px, py, and pz, but all points in the sphere have the same total momentum magnitude of p. So if you track the magnitude in this sphere as the particle bounces around in the cube while the energy is conserved, you can see there is always a point on the sphere to describe that momentum vector. How does this relate back to the energy probability equation? Well, if the energy of the particle is the combination of each of the momentum components squared over 2m, we can create a new probability equation that finds the probability of a particle existing with a specific combination of px, py, and pz values that looks like this. But what does this mean? Well, if we take this sphere, and as the momentum changes to different directions, we see the different microstates change, but the total magnitude of the combined momentum remains the same. Since the probability of a specific combination of px, py, and pz values existing is related to the energy at that configuration, which is determined by the total momentum, and the total momentum remains constant for each possible configuration, that means every possible configuration of momentum components on this sphere have the exact same probability of occurring, because they have the same energy. If we take a deeper look at the equation that governs this, it has some special properties. Exponential equations have a special property where if the exponent is a sum, the result becomes a product. This allows us to separate our equation into 3 independent exponents, each representing a different momentum component. So let's take a look at what this probability distribution actually looks like. If we create a px, py, and pz axis and plot the probability distribution on these axes, you can see that the smaller the momentum, the higher the probability density, and this probability density decreases as the momentum increases. But momentum distribution across all 3 dimensions is quite abstract. If we want to make it something more tangible, it would be good to look at the distribution of momentum in just one direction, for example the x direction. How can we do that? Well, let's take one value of the x dimension and take a slice out of this distribution. This gives us the plane of distributions of momentum in the y and z direction, all of which are possible for this specific px value. So to find the probability density of this px value in particular, we need to find the total value of this entire slice of the plane. Each of the py and pz components has the form e to the power of minus x squared, an exponential of a squared quantity with a minus sign. Any function of this form is called a Gaussian. It produces the familiar bell-shaped curve, highest at 0 and falling off smoothly on either side. And we need to integrate them both to find the product of both integrals to find the total value of the plane slice. But Gauss has already proved that when you integrate a Gaussian, you simply get a constant. So integrating them both and multiplying them will just give us another constant, independent of either py or pz. How do we know this? Well, Carl Gauss in 1809 was tasked with finding the integral of this Gaussian equation and proved that it's a constant, the square root of pi over the constant factor in the exponent's power. But that's a whole different story. Take a look into the Gaussian integral if you want to try and prove it yourself. But that's not too important right now. What is important is that we know that both the integrals are constants, and the product of them both will just be another constant. So if we go back to our 3D spherical distribution, we can say that the value of that plane is c. So if we wanted to plot the probability distribution of just the px component, we would see that it's proportional to the part of the equation that includes the px component, the Gaussian of px, and then the constant c to represent the sum of all the values on the plane for that value of px. Again, when plotting this, it's just a Gaussian distribution. And since this relationship is showing how the probability changes proportionally with momentum in the x direction, that constant can be factored right out. So this leaves an independent Gaussian distribution to determine the probability distribution of momentum in the x direction. This is the same for the y and z direction too. So let's pause and look at what we've actually discovered here. Starting from Boltzmann's exponential law, we found that the total energy splits into 3 independent quadratic pieces, one for each spatial direction. Because exponentials turn sums into products, the full 3-dimensional distribution factorizes into 3 independent Gaussian distributions. The momentum in the x direction is statistically independent from the momentum in the y and z directions. And not only that, all 3 directions are governed by exactly the same distribution. No direction is preferred. The system is completely symmetric. So the fact that these distributions are Gaussian allows us to find more information. A feature of the Gaussian is that the mean value of each distribution is 0, but the mean squared value can be calculated based off the coefficient of the exponent's power. It is half of the inverse of the exponent's coefficient. This is straight out of probability theory from the 18th and 19th centuries, so simply because these distributions are Gaussians, we can also show that the mean squared values are the mass divided by alpha. And we can now do a bit more algebra. Since the average energy in each direction is the average momentum squared in that direction divided by 2m, the kinetic energy, we can merge these two equations to give us this. The average energy in each direction is equal to 1 over 2 alpha. It's constant in every direction. This is the basis for what we call the Equipartition Theorem. But more on that in a second. For now, we can say that the average total energy of a particle is the sum of the average energy in the x, y and z directions, which gives us the formula for the average energy being 3 over 2 multiplied by 1 over alpha. So now we have a formula for the average energy per particle that depends on this variable alpha. So we now have 2 equations that tell us important information about the thermodynamics of a system. One about the average energy of a particle within a system, and one about the probability of a particle being at a specific energy level. Both of them involve the variable alpha. But what actually is alpha? That's what we need to take this from theory to reality. So let's imagine a particle in a box moving with momentum px. Kinetic theory tells us that the pressure is proportional to 1/3 of the number of molecules per cubic meter volume, and the mass of each particle, as well as the mean square velocity of each particle. We also know that kinetic energy is half mv squared, so we can combine there to show the mass times the mean square velocity is equal to 2 times the average energy. And plug this into the top equation. This relationship comes from kinetic theory, first suggested by Daniel Bernoulli in 1738, and later developed by Clausius and Maxwell. And now, if we combine this equation with our other ideal gas law equation, PV equals nKT, we can use some algebra to show that the average energy of a particle is equal to 3/2 kT. So a lot of algebra there, but now we bring this back to our original equations. We can derive alpha. By setting both average energy equations equal to one another, dividing by a factor of 3/2, and rearranging for alpha, we find alpha to be equal to 1/kT, where K is a constant and T is the temperature. This can be plugged into the probability equation to give us our final distribution. The probability of energy E is proportional to the exponent of negative E/kT, and it can be also plugged into the average energy equation to show the average energy of a particle is 3/2 kT. So what are the implications of this? Well, first off, we have the Equipartition Theorem. The average energy is 3/2 kT, and this is because there are 3 degrees of freedom for a particle that have independent quadratics. Each of these independent quadratic degrees of freedom contribute to the total energy and have an equal share of the energy split. So what if there was only 1 degree of freedom? For a particle that could only oscillate in the x direction, for example, its energy could only be distributed across one quadratic. The average energy would be 1/2 kT. Then with another degree of freedom, the particle could oscillate in both the x and y direction. The energy would be distributed evenly across them, and the average energy for the particle would increase to 2 kT/2, or just kT. Then we can add a third degree of freedom, and this adds another quadratic to the energy equation. The energy will be distributed evenly across it too. And for example, if there was a 4th degree of freedom, such as the rotational energy, since this would add a quadratic component to the energy equation, it too would get an equal share of the energy to the other degrees of freedom. This is the Equipartition Theorem, and it's the real takeaway of this video. The full formula and definition for the Equipartition Theorem is here. If a system has F degrees of freedom, then the average energy of that system is proportional to the absolute temperature, the Boltzmann constant, in F divided by 2. In the next video, we are going to go into the ultraviolet catastrophe, which sets the scene for quantum physics, and it's beneficial to have a basic understanding for the Equipartition Theorem to properly digest it. So for now, we are done with Boltzmann. But to conclude this chapter on Boltzmann, his ideas change the way that we can perceive and measure reality. If I asked you to guess which of these pots this ball would fall in, there's no way you could tell. If we plotted the distribution after 1, there would be no pattern. But as we add more and more balls, the distribution becomes more and more recognisable, until it settles on a normal distribution. And when we are looking at the system as a whole, we can make predictions based on this, such as the average position, the probability of each position being occupied, or the standard deviation of positions. Even if things seem completely random on a microscopic scale, when there are a collection of units operating like this, microscopic natural patterns emerge, and statistical laws are upheld. Order emerges from the chaos, and the laws of thermodynamics reveal themselves to be laws of overwhelming probability. Thanks for watching, and I'll see you in the next video about the ultraviolet catastrophe.